small l. So small l. Right. So instead of force, I will write Young's modulus as WL by A small l. Then it says if some wire is passed over a pulley and two weights each are used, mean this is, suppose this is the, here you have the pulley. Here you have the pulley. Now it says if some wire is passed over the pulley and two weights W each are hung at the two ends. Here one W is hung, here also one W is hung. Then it is asking what will be the total elongation of the wire. See what will be the total elongation of the wire, how much it has elongated. This part will be L by 2. This part will be L by 2, right? So if you just take out one part of it for W, what will be the Young's modulus? Young's modulus will remain the same. W will be there. Length will become C. Here the length will become L by 2, right? Length will become L by 2. Area of cross section A, and the length that it increases, that we do not know. We have to find total elongation only. Let's say delta L. Right. So from here, this is if you take the ratio of all these, or even if you equate it, WLA small l, it will be equal to WL by 2A delta L. See, A, WL, WLA will get cancelled. Delta L will become small l by 2. Right. So elongation in this wire is coming L by 2. Right. So total elongation it is asking. Total elongation in this entire wire will be, here also it will be L by 2. So total elongation will be L by 2 plus L by 2. Total elongation, this will be L by 2 into 2 directly 2, or L plus L by 2 by L by 2. So this becomes L. So total elongation also comes L. Then we'll start with the next type of moduli of elasticity. By the time, just note down this, and any doubts you're having from the previous topics, please let me know. We'll try to complete this lesson today so that we can start with fluids next. Second part, okay, from here. See, this means what? If you take the string and you tie it on a pulley, then the half of the length will be available to you here. So this is L by 2. When you put the length as L by 2, you get the relation of elongation as L by 2, small L by 2. It means here delta L is L by 2. Let me tell you this. See, this L by 2, this is actually the total length by 2. You can make it as capital L also, capital L by 2. This length is capital L by 2, capital L by 2. Whereas after this calculation, the elongation comes out to be delta L by 2. This is delta L, L by 2. So if this side is L by 2, this side is L by 2, you will get total elongation as L. Understood? Or should I repeat once more?
Yes, misunderstood.
Okay, okay. If you all have written, can we start with bulk modulus? Because this part, stress strain energy curve, this curve is not part of your syllabus now. Bulk modulus, let's see. So see, when there was a change in the length, we got Young's modulus. Please remember this class. Now, second is change in volume. So volumetric strain you had, volumetric stress you had. Remember, both of it you had. Volumetric stress is what? Normal stress only because the force was applied perpendicular. So volumic stress and volumic strain, their ratio will give you bulk modulus. So where will be the change that you will observe? It will be in the volume. So bulk modulus is represented with the help of beta most of the time, or many a times it is represented by capital B. So we'll also use capital B only. So capital B or sometimes K or sometimes eta also, but eta will use it for shear modulus. So B is fine, bulk modulus. So this is ratio of normal stress, or you can take volumetric stress. Volumetric stress volumetric strain. So here also, see, this SI unit of stress will be force per unit area, SI unit of pressure, that is Pascal, and strain, this is the ratio of same quantity, it has no units. So SI unit of bulk modulus will be Pascals. Now formula of bulk modulus. See, volumic stress. Volumic stress. Volumic stress is again force per unit area. Or pressure, directly you can write pressure. Here writing pressure is much better. And then change in volume by original volume minus P V by delta V. This is the formula of bulk modulus. SI unit will still remain Pascals. Fine. Now here you have one more topic, that is compressibility. Compressibility means how much a material can be easily compressed. Like if the compressibility of a material is high, you'll be able to compress it more. So compressibility, mathematically, you represent it by K, which is inverse of bulk modulus. This K is compressibility. B is bulk modulus. K is compressibility and B is bulk modulus. So SI unit, when you write the SI unit of it, SI unit will be inverse of Pascal. SI unit will be Pascal inverse. Okay, let's see some questions. Note down these 2 points first. Bulk modulus. Remember, related to volume always. This is a very easy lesson. After this, you just have one type of modulus, shear modulus, and then energy part. See, there's one formula that will help you in this question that we are going to do in solids. P is equal to H rho G. There's a derivation also of this formula that we are going to do in the next lesson. Because here pressure will be needed and you have to calculate delta V by V. Bulk modulus is also given. See, bulk modulus is minus P. Okay, one more thing I didn't discuss. Why is this minus sign? Minus sign simply indicates that volume is decreasing. Nobody asked me about the negative sign. See, minus sign is just because this volume is decreasing. In case of length, length could have increased also. Here volume is decreasing. All right, that's why we have a negative sign. So minus P delta V by V. So delta V by V will be, now just take the magnitude, P divided by B. But here we do not have pressure. But we have the height. Height is 3000 meters. So if we use the formula and apply this formula derivation is also there in your syllabus that we are going to do in the next lesson. Don't worry about this. This is the pressure exerted by water column. Fine. So this is H rho G. H is the height, rho is the density, G is acceleration due to gravity. So it is mentioned Indian Ocean, average depth of Indian Ocean. It means it is talking about water, and water density is 1000 kg per meter cube. This is that has been written by me. This is not a part of question. So this you have to remember the density of water in both SI and CGS unit. Now delta V by V. Pressure will be H rho G divided by bulk modulus. This is what you have to calculate. So see, delta V by V. H is 3000, density is 1000. Take acceleration due to gravity as 10 only, and bulk's modulus as 2.2 into 10 to the power 9. So this will be 6, 7, 3 into 10 to the power 7 divided by 2.2 into 10 to the power 9. It is fractional ratio, volumes SI unit will be cancelled. Whatever you get here, that will be your final answer. Write down the solution. not around 6.6, around 2.3, 1.3 something. Just check once again. Till the time, just note down this question and write, then we'll discuss this. Then we'll move on to the last modulus. And those who are getting this answer, please let me know. This says that if normal density of seawater is 1 gram per centimeter cube, what will be its density at a depth of 3 kilometer? Compressibility is given to you 0.0005 per atmosphere. So if you want, you can convert it also. See, then we'll discuss it. See, it says that if normal density of seawater is 1 gram per centimeter cube, what will be its density at a depth of 3 kilometer? So density is given as 1 gram per centimeter cube. Height is given 3 kilometers. It's better if you convert this. See, 3 into 10 to the power 3 meter. And if you convert this, you will divide it by 10 to the power 2. So that makes it 3 into 30 centimeters. Right. So now 300 centimeters. Okay. Then it says compressibility is given. No, compressibility is given. So here you have the value of K 0.00005 per atmosphere. ATM is also the SI unit of it. So 1 by bulk modulus is K. So bulk modulus will be 1 by K. See, bulk modulus formula. This is minus P delta V by V. Bulk modulus can be given by 1 by K from the formula. And atmosphere is also given. You can also convert this into centimeters so that every unit is in SI. So normal density, we know 1 gram per centimeter. So same thing for pressure, pascals, you will use H rho G, same thing. This will be H rho G. It's just that everything will be in centimeters. Understood? See, P is equal to H rho G. Height is given 3 kilometers. Density is 1 gram per centimeter cube and G is 10 meter per second square. See, all are in different unit. One in meter, other in centimeter, one is kilometer. Convert all into centimeter, put it here, right? And then you have the bulk modulus with you. So you have to find out the density at that length. Note down this, then we'll start with shear modulus, the last topic. See class, now last topic that was left, see, change in length, Young's modulus. Change in volume, bulk modulus. Now change in shape. Remember, change in shape, if you apply a force that is parallel to the surface. So that is shear modulus. So it is defined as the ratio of tangential stress to the shear strain. Right? Now see, shear strain and tangential stress. So tangential stress, this is still equal to force by area. And remember theta, shear stress, which we saw, shear strain, that was equal to delta L by L. So the formula of shear modulus, this is represented by this symbol eta. This is exactly same like Young's modulus, F by A delta L by L. Same thing with SI unit as Pascals. Noted down, then let's see some numericals on this. This is all about the theory of it. We have some numericals we'll see. Then we'll discuss one more thing, energy. Then that will finish this lesson. It's a very short lesson, very easy questions come. The questions that we are discussing in the class now, that are even difficult. The questions that will come in the exam will be very basic and simpler than this. We are actually trying to discuss the questions that have a little difficulty. In the exam, the questions will be direct formula based. So please try to learn the formulas and definitions of all the stresses, strains, and moduli. Note down this question. See, a 0.05 meter cube has its upper face displaced by 0.2 centimeters. This means this part here, the force gets applied. And like this, the face gets displaced. And this is 0.2 centimeters. Force is 8 Newton, modulus of rigidity. Quickly calculate it. Send me the answers. 2 minutes and I'll discuss it. Yes, for your calculations, you can take it like this, Tari. See, this is the length of the cube. Right, this is the length of the cube, 0.05 meter. And this is the displacement that occurred. So this is delta L. This is L. Force is 8 Newton. Right, and this is a cube. So you know the area of the cube also, 0.5 whole square. So when you will put for modulus of rigidity, force into delta L, 0.2 into 10 to the power minus 2. area 0.05 whole square into the change in length. Okay, change in length I will tilt here, no? See, this will be the change in length. Delta L will come below. 0.2 into 10 to the power minus 2, and this is L, 0.05. So 1 square will get cancelled. How much are you getting? 8 into 10 to the power 4 Newton per meter square. Someone check, are you all also getting the same? But this question is very simple. See, this has slid away. This upper part has displaced. So this is the change that has arisen. This is the only type of question that you will get in exam. This was the original length. Force you have. Area you can calculate. Right. Quickly note it down. One more question we'll see. And then we'll move on to the last topic. It says that two strips of metals are riveted together at their ends by 4 rivets. So each rivet's diameter is 6 millimeter. You have to find out the maximum tension, means force you have to find out. Force is missing and shearing stress is given. Now here the force that you will take, no, because 4 rivets are given. So force on each rivet that you will take will be F by 4. F is the force applied on the metallic strip. So for each single rivet, when you calculate, it will be F by 4. So here shear force F by 4, then area into change in the length by original length. This is how you will write it. So see, area is given, and here you have shearing stress with you. Shearing stress is mentioned, and you have to find out maximum tension. So two strips of metals are riveted together at their ends by 4 rivets, fine. And diameter, each of diameter 6 millimeter. So radius will be 3 millimeter. So area will be pi r square. What is the maximum tension that can be exerted by the riveted strip if shearing stress on it is given? So here you don't even need to use this formula. See, shearing stress will be force by area, and force is F by 4. So from here, force will be 4 into A into shearing stress. So force will be 4 into area will be pi into 3 millimeter whole square. This is the area, right? Diameter is 6 millimeters. Of this one single rivet, the diameter is 6 millimeters. So radius will be 3 millimeters. So area will be pi r square. And shearing stress is given how much? 2.3 into 10 to the power 9. 2.3 into 10 to the power 9 pascals. So entire unit will come out to be in terms of Newton. This much Newton is the answer. All right, copy it down. Question I hope you all have written. Just solution part you have to write. Note it down. See, strain energy. The formula of strain energy means whatever work done you have to calculate. So first thing that you have to understand over here is the formula of it, that is energy. Energy's formula is simply half into stress into strain into volume. Stress, you know, all the three types of stress, so any of it will work. Strain, same goes for strain, any type of strain, and then the volume. Now, if you bring this volume down here, if you bring up this volume over here in the denominator, so that will be energy per unit volume. So energy per unit volume is this represented by the symbol U only, a small u, that means half into stress into strain. So strain energy is asked, you will use this. Energy per unit volume is asked, then only you'll use half into stress into strain. Fine, this is what is meant by simply work done in the body. The elastic energy will be storing itself in the form of potential energies. So that work done, that is stored in the form of energy. This is known as elastic strain energy. Right, one ratio you have, this ratio is also easy, this ratio. See here, this is known this is known as Poisson's ratio. This is actually the ratio between two things, lateral strain and longitudinal strain. So it is also unitless because strain will get cancelled. Now see what is meant by lateral strain. Lateral strain means in the girth when the length increases. Sideways in the girth means thickness is increasing. The way, no, how is a tree's trunk and stems different? In girth only, laterally, trunk has more length or more girth or width, you can say, than a thin stem. So that strain that is obtained, sideways strain, that is known as lateral strain. So lateral strain's formula is minus delta D by capital D. Delta D is the change in diameter, capital D is original diameter. Like change in length by original length we are writing, similarly change in diameter by original diameter. So minus delta D by capital D. Now Poisson's ratio you have. Poisson's ratio is lateral strain by longitudinal strain. Now longitudinal strain is what? Longitudinal strain we have discussed, the ratio between the length. So lateral strain is something new. Lateral longitudinal you already know. So complete Poisson's ratio will be minus delta D L by D into delta L. Same formula, same thing, just that you have a new strain, that is lateral strain. Now see, this part is just from your numericals part. See, just to remember these 2 points, the Poisson's ratio cannot be more than half. It has to be 0.5 maximum. Usually it is between 0.2 to 0.4, 0.23, 0.39, like this you'll find the Poisson's ratio's answer. Now, these 4 points are just certain relations. These are not very much helpful for you, I'll tell you. You have to apply proper formula and see, these are just shortcut values. Sigma is Poisson's ratio here, B is bulk modulus, Y is Young's modulus. These are more helpful for students who are preparing for their entrances, for those who have written this. So you can write it down. Wherever you are required to write it, you can copy it. Otherwise, I'll not suggest any of you to learn any of these formula. Main formula you have to remember, that will only be helpful. Note it down. Any doubts you have while writing this? See, B is bulk modulus, sigma is Poisson's ratio. This N type symbol, this is eta, which is shear modulus, Y is Young's modulus. Like if you have bulk modulus, shear modulus, and Young's modulus. So a relation between these will be 9 by Y is equal to 1 by B plus 3 by eta. Fine, like this you have the relations. So you can note it down just in case if it is required by you. Otherwise, no need. Note it from here. Any doubts you have, text me, ask me, get it clear. Because after this, we have to start with fluids. This was a very short lesson. Then your bulk properties will be over. If you have noted till here, then you can leave. That will complete with mechanical properties of solids. Then we have